So, again, tightly packed, very close together, ordered efficiently, geometric patterns. And what are they doing? They're not moving around, they're doing what? Vibrating. That's what made me think of the dog. So they're vibrating, okay? These particles are vibrating, that's what those lines, so the particles just sit there and shake, okay? So the story about the dog, this dog was a Jack Russell Terrier, his name was Baxter. He would just sit there, stare at you and shake because he wanted you to throw something that he could go get and bring back to you. He was one of those dogs where you could literally play, whatever, not catch, but whatever. Fetch, yeah, I guess. Throw the ball, he'd go get it, he would do it literally for 6 hours straight. So he was kind of spastic. I thought he was a demon, and then this story proved it. Yes?
Did you kick him in the protons?
I did not kick him in the protons. What is that from?
From If You Can.
Yeah, but why did I say that? Who said that?
You said it.
I said it?
You're like, if I have a dog, kick him in the protons.
That's kind of funny. I thought someone else said that. Anyways, no, that's mean. I don't hurt animals, but it was funny. So the dog was sleeping in front of a fireplace, okay? My friend's fireplace, and he didn't pull the screen closed. So you know how the wood pops sometimes? The wood was burning, it popped, and like a glowing orange ember like bounced out right in front of the dog. So the dog's just laying there. Dog picked his head up, ate the ember, and went back to sleep. Glowing orange. Didn't flinch, didn't make a noise, went right back to sleep. Straight up devil dog. Okay? Demon dog, I call it. Unbelievable, and I can't believe the dog survived. I mean, the dog, that should have burned a hole right through his esophagus or his mouth.
That's what.
Yeah, the dog freaked me out. Plus, the dog would just always stare at you.
Was it ugly? Was it ugly too? Or?
No, it looked like a Jack Russell Terrier. So that's the story. Back to this. So solids. Know how to draw it, know how to explain what they look like, but we also have to write down, does it have definite volume? Yes, it does. Definite volume, what does that mean? The volume of a solid does not change. Whether you put it in a big container or a smaller container, take it outside, bring it in, whatever. The shape and volume, we're going to write shape, but the shape and volume are definite. They do not change. Definite volume and definite shape.
That dog's got some protons, man.
Yes, it does. Actually, no, it didn't, because it was neutered. But so, anyways, definite volume, definite shape. What does that mean? The shape doesn't change, and the volume, the amount of space it takes up, doesn't change. Why? Here's why. Particles are really, really, really close together. So if you try and compress a solid, will you have a lot of success? No, because what happens to those particles if you put force on them? Well, they may break, but let's assume they don't. What are they going to do? Yeah, they're just going to hit each other. They're not going to go any further. Okay, these desks are fairly close together. Okay, if I push them together, they're going to stop. They're not going to go any further. That's what these atoms do. When you start pushing and putting force on a solid, it'll only go so far, and that distance is tiny because the particles are so close. So what we're going to write is the solids cannot be compressed. That word is cannot. Sorry, it looks like an M. Cannot be compressed or expanded. Actually, they can't do either. You can't take a solid and get the particles to spread out from one another. And the same explanation. Due to the particles being too close together. That's why they can't expand, that's why they don't compress. Okay? Kids are like, what about trash compactors? Yeah, you can put something in a trash compactor, but once all the space is taken up and you get down to the solid parts aren't going to get compressed any further. Okay? Because the particles are very close together, there's no room for them to move.
Do a Sharpie.
You got it.
I didn't want to get your video.
Yeah, I don't want you to interrupt it, Maureen. There you go. Okay. cannot be compressed or expanded. Why? Again, particles smash into each other if you're compressing, and if they're trying to expand, they smash into their neighbors, right? Where's this one gonna go? Nowhere, okay? It has nowhere to go. That's why it has definite volume, definite shape. Okay, next, liquids. Oh, and again, make sure you wrote down that the particles are vibrating. I'm not writing everything down. You should be writing some things down too that I don't. So, they are vibrating. All right, so there's the solid. Oh, where the heck is it now? This one? There it is. Okay, so there's the, there's the liquid. Okay, so liquid particles are a little bit further apart. I don't like this picture. I told you that yesterday. I don't like the picture, but it's still good because it's different than a solid. The solid were packed in rows like a cube. These are kind of random. All right. Liquid particles, they're a little bit further spaced out, just a little, and they're able to flow and move around. So liquid particles flow. Okay, they flow. Think that word meaning motion. They don't just vibrate, they move around. Okay? What about volume and shape for liquids? Anybody? Volume and shape for liquids. Raise your hands. Liquids have definite volume, or does the volume change? Yes, sir. Definite volume or not? Or you're unsure? What do you think?
They don't have a definite volume
Why not?
because they changed the object that they're inside of.
So if I fill this up with 32 ounces of water and I pour it in a bigger container to fill up the bigger container? No. Well, will I still have 32 ounces? Yes, good job, Jake. You helped us out. Thanks for sharing. So, definite volume. Definite volume. So the volume will not change just because you put it in a bigger container. Definite volume. What about shape though, Jake? I think that's what you were thinking of. Shape will change, right? So if I fill this up, the water in here takes the shape of this container. If I pour it into a big tray, okay, that's just a thin or thick enough to hold all the water, but it just will fill the tray. It'll be in the shape of the tray. And if we pour it on the floor, it'll spread out and kind of take the shape of a flat floor. So the shape changes, definite volume, but the shape changes, and that's because the particles can move around. They can flow around each other, move around a little bit. Okay, but again, the spaces, again, this is not a great picture. All right, spaces are not this big, not relative to that other picture. Again, I use it just because it is a good image. It's just, it should be a little closer together. So definite volume, shape changes for sure, depending on, I should put that, depending on the container. Shape changes depending on the container. All right, can you expand a gas? Can you, or not a gas, a liquid. Can you compress a liquid or expand a liquid? What do you guys think? Can you make a liquid take up less space than it already is taking up? The answer is on the board. No, definite volume. You can't make it take up more or less space. Why? Here's why. Look up here. If these are solid particles and are this close, liquid particles are like that close. They're just a little bit further apart. So even if you try and expand or compress liquids, particles run into each other. So liquids cannot be compressed or expanded. You can't expand a liquid either. But wait a minute, there's always somebody who says, yes, you can. You can do this. What can you do to a liquid that appears as if it's expanding, but it's not the liquid? Okay, freeze it. If you freeze water, it does expand. Ice expands, that's why it's less dense. We'll talk more about it down the road. But it's the solid ice that's expanding, not the liquid. What about when you boil water? Aren't the particles expanding, turning into a gas? Yes, but the gas is expanding, not the liquid. So liquids don't expand, they don't compress. When they turn into a gas, that's a different story. That's next. But the actual liquid, particles are too close together. Particles are too close together. I feel like I'm forgetting something. I gotta check my notes every once in a while instead of doing it all off my head here. Off the top of my head. Okay, nope, that was it. Okay, last one. Gases. All right. That's my email. Here we go. This one again. So, what do we notice about the gas particles here? This is what gas particles look like. What do we notice? What are they doing? Someone shout some words out there. They're moving. How? Fast, quick, good. Does it look like any one of those particles has a course of action in mind, or is it kind of random? Do they look like they're moving random, or are they repeating?
They're repeating.
Well, technically in the video they were repeating.
No, in the video they're repeating.
Not really.
Yeah, there's one that just keeps doing the same thing.
Bet
Oh.
if we watched it enough times, we would repeat.
I was looking at it.
Oh, dang
You can hit the replay button right there.
Some of them may appear to be repeating. I don't know. I haven't stared at them long enough. But in real life, the motion is random. Okay, that looks pretty random to me. If I saw a bunch of people doing those things, running from like above, I would say they're running in random motion, right? So there's no order or pattern to that at all. So you should write all these things down. How do they move? What did we say already? Randomly. What else? What other words did we throw out there? They move fast, they move quick. What else? I think Devin said it. What'd you say? Straight lines. So they move in straight lines. They move in straight lines. I'm just going to pause it. They move in straight lines. They move fast. They move quick. Either word. They move randomly. Okay? Random straight lines very quickly. How could we speed up how fast? See you, Sarah. How could you speed up how fast they move?
Heat
Heat it. What do you want to slow them down?
Freeze it.
Right, cool it down. Okay? What do you notice about gas particles that's different than solids and liquids?
They're spread out.
Yes. Particles in a gas are very spread out. Very spread out. Guess what that means? Guess what that means, Blake? Can we compress a gas easily?
Yes.
Yes. Why, Blake? Right. Okay? If I'm leaning on the board, I don't really want to get my dirty shirt, my shirt dirty. But if I'm leaning on the board and I want to get closer to the board, I can't. I'm already leaning on it. That's a solid, right? Liquids aren't much better. But if I'm a gas particle and I'm standing in the back of the room and I want to get close to this wall, I have all that space that I can move. That's the same concept. If I want these two particles to get closer together, I can do that. There's space. They will move. So because particles are spread out very far apart, particles are very spread out, gas is easily compressed and easily compressed, easily expanded. They easily expand. You're doing it right now when you breathe. When you breathe air in, what are you doing to the air? Compressing it or expanding it? When you're breathing it in, you're compressing it. The room is enormous compared to your lungs are like this big. Okay? So the room is way bigger. So you're taking a deep breath, taking all this space, all right, as much as you can in front of your face, and you're compressing it to fill your tiny lungs compared to the room. When you exhale, all that gas that was compressed is now expanding throughout the room. So whenever you breathe, you're doing both of those. Compressing, expanding, compressing, expanding. That's actually called Boyle's Law. It's a pressure-volume relationship. We'll talk later in the year. But the pressure builds up, and you have to think about breathing. You have to tell yourself, exhale, inhale, exhale. No, if we had to do that, most people probably would die. We wouldn't survive as a race. Or not, yeah, I guess a race. So the concept I'm trying to get you to understand is your body does it naturally because this is natural, and this is easy. It's easy for gases to compress and expand, and has a lot to do with the pressure that builds up. Once the pressure in your lungs builds up, it wants to get out. So it just does it on its own. You don't have to think about it. So anyways, hopefully that makes some sense to you. Now the last thing with these three, you can leave the lights off. No? You're not going to turn off on me here? Okay. All right, the term forces of attraction. Forces of attraction. Kind of like gravity. When two particles are near each other, they exert some sort of attractive force on each other. So let's think of it this way. If the sun, so stay with me, here's the analogy and then I'm going to ask a question. If the sun's gravitational pull just all of a sudden, I snap my finger, increased by about 100 billion times what it is now, what do you think could happen to the Earth?
It would just destroy. Be destroyed.
I need someone to explain it better.
Pressure.
What are we doing around the sun? What's that term? Right, why are we orbiting the sun?
So you get like heat and light and everything.
Because of gravitational pull.
Well,
The sun is pulling on the Earth, keeping it near the sun, but not pulling it into the sun, because then we would die. So if the sun's gravitational pull increased dramatically, what would happen to the Earth? It would get sucked right into the sun. Does that make some sense?
Yeah.
Okay. What if the sun's gravitational pull ceased to exist? I snap my finger, no more gravitational pull from the sun.
It'd be mad cold. It'd be
What would happen to the Earth? Yeah, we would just fly off into space, okay? Now, which phase, solid, liquid, or gas, based on the analogy with the sun and the Earth, which phase, solid, liquid, and gas, raise your hands, and you guys need to start participating more. Just sit here and stare at me. Which phase, solid, liquid, gas, has the strongest forces of attraction, based on that analogy with the gravity and the sun and the Earth? Or, if you want to explain which one has the weakest force. Go ahead, Ryan.
Solid, because it's like the most.
I need you to, which one are you answering?
The strongest.
Yes, very good. Write this down in your notes. Solids have the strongest forces of attraction. Tell me why, Ryan?
Because they're like they're closest together.
Very good, because the particles are close together. Particles are close together. All right, trick or tough question here, not trick question. Charlie, which phase has the weakest forces of attraction?
Gases.
Very good. Gases have the weakest forces of attraction. Why, Charlie?
because the particles are spread out.
Very good. Because the particles are spread out, far away from each other. Think about real life. Think about people, men, women, boys, girls. If you're attracted to someone, you want to be right near them all the time. Makes sense. Solids. If you're not attracted or you really dislike somebody, you're not going to want to be near them. You can be far apart. So I always say, gas particles hate each other, solid particles love each other. Okay? Makes sense. There's an attraction here. It's strong. So they're close. No attraction. They could care less. They get away from each other. Okay? So remember that. You'll be in good shape. Questions? Okay. I think my eraser is dirty or something. I don't know. All right. Back to the pictures here. I got something else here to show you. Images, and then we're gonna move on. All right. Let's see. Where is that? All right. I'm gonna show you a picture of my bedroom.
This is yours.
Yep. There it is. Look how nice and rich I am. Just kidding. Not my bedroom. I don't even know if I would like a bedroom like that. It's a little too like for me, but like sterile,
It's kind of open too.
like robotic. Like it's like whoever lives in this type of place is like too clean for me. Even though I do like clean stuff. Anyways, point is, notice this bedroom. Okay, very nice, clean, organized, not a lot of clutter. Okay, and I also have a picture of Zach's bedroom.
Sweet.
There's Zach's bedroom. Okay, Devin gave him that purse for his birthday. So the teddy bear Okay, he has that too.
Okay.
Notice all of the clutter in this room, not so organized. Okay, there's a reason for this. I'm not just making fun of Zach. All right, there's a reason for this. Write this word down. Entropy. Entropy. Write this down. Entropy. 2 stars. It's an important term. You got to know this the rest of the year. You got to know what entropy means. Okay. So based on these 2 rooms, and I'll give you another example and see if you can figure it out. This room has high entropy. Oh, did I close it? Nope. That room has low entropy. So low entropy here, high entropy here. Let me give you another example. Right now, in class, you guys have low entropy. When the bell rings, you're going to go out in the hall, and the hallways have very high entropy. Raise your hand and tell me, what do you think that word means? Someone besides Ryan. Go ahead.
How much clutter is in there?
Clutter. Give me another word.
Crowded. No.
Crowded. Okay. The
Dense.
degree.
Great words.
Write this down. The degree of. I'm going to give you a simple answer, but these are all good things. Yes, things with entropy, high entropy, have a lot of clutter. They're crowded. Think of the hallways, because I can't show it with the picture here. What does the hallway have? A lot of what? During class changes.
Kids.
A lot of clutter. Okay. What else? What are the kids doing?
Yeah.
Moving. A lot of movement. Okay. A lot of movement. So crowded, cluttered, movement. Chaos is the word. Lots of chaos. This is the degree of disorder. That's if you were to look this up in some chem books, all right, textbooks, it would say degree of disorder, or we could say chaos. Okay? So all the other things some of you were saying, that's fine. Those are good words, but the degree of disorder. So why am I showing you the bedrooms here? Just to give you a concept of kind of what this word means. So the more entropy, like this room, high entropy. So, solids and gases. Let's relate it to what we just learned. Which one, raise your hands, or I'll call on someone if I have to, which I might have to. Which one has low entropy? Which one has high entropy? So, I'll give you a hint. This is kind of randomly organized, if you want to call it that. It's a nice way to say messy. This one is very ordered, not so random. Go ahead, Nicole.
Gases have high entropy.
Yes, gases have high entropy. Those particles bouncing around have no idea what they're doing. They're just randomly bouncing, moving quickly, very far away, slamming into the wall, slamming into each other. Solids just sit there. They vibrate, they just sit there. So, Nicole finished. Solids have low entropy. Because they're very organized, right? If this measures disorder, solids aren't disordered at all. There might be a lot of particles clustered together, but they're ordered in rows, patterns. Gases, kind of crazy, no order, random, high entropy. Make sense? Now that you know what the word means, hopefully. Okay? All right. So, we're done with that. Lights, please. Can I erase that? We're good? Next. That one's even worse. Next. Left side of your paper. You're going to need at least half a page, maybe. Left side of your paper. Physical changes / properties. Okay, then go over to the right side. Chemical changes / properties. And you will have a worksheet for homework on chemical physical properties and changes. And again, I'm teaching a little bit out of order. You probably don't notice, but I'm explaining it anyway. I want to talk about elements, compounds, in mixtures tomorrow. Probably should have done that today, but I really want to make sure we understand this first. Because if you don't understand what physical and chemical means, tomorrow's going to be confusing. So I switched it up this year. Not that you would know any different, but I'm just explaining that. All right, who can tell me? We talked about it in lab. Everybody in here should know the difference. If you see a physical change occur, what does that mean? Go ahead, Ryan.
There's no change in the chemical composition.
Very good. So this is a change or observation, we can say, right? So maybe if you make an observation is a better way to say it, but a change or an observation where the substance does not, underline not, probably should capitalize it too, does not change its composition. So the composition stays the same. Composition does not change. What about chemical change, Ryan?
Something that the chemical composition does change.
Yeah. So it's a change that occurs, change or observation, where a substance's composition changes. And that's it. That's the two basic, simple differences between physical and chemical. If you witness or observe a chemical change, the composition, a brand new substance is going to be produced. Something new, something you didn't start with, like those demos in the fume hood. Fire, smoke, light, color changes. We're going to be listing all this. But something new, that's how you know something new is being created. I did a physical change, only one physical change with the whole lab class when I was making a stirring rod. What did I do? I cut it, broke it, that's all physical. That's easy, you know that. If you break a piece of glass, it doesn't turn into like a dove and fly away, okay? It's still a piece of glass, so breaking, you know that. What did I do to it though so it wasn't jagged? I did this in the flame, what was I doing? Melting it, right? It wasn't burning, it was melting. So phase changes. Phase changes do not alter composition. What does that mean? Melting, boiling, freezing, condensing. What about dissolving? Is that physical or chemical? Who remembers from lab? We talked about this. Kristen, remember? Physical, right. Dissolving is a physical process because you can get the substance back by evaporating the water. It doesn't change. Over here, some chemical changes. A new product is formed, like we did in lab today and yesterday. Well, the group from yesterday you'll see tomorrow morning. But they change. That aluminum foil turns into something new. New product. How do you know? Color change. Fire. Smoke. Light. Odor change. Okay, go run around the school a few times. You start to sweat, you might start smelling. Odor change. Well, at least you might smell your deodorant. You're supposed to be wearing that. But the only reason deodorants work is because they work based on chemical reactions in your armpit. Odor change. What else? When I mix those two colorless solutions the first day of school, form that yellow stuff. What was that yellow stuff? Solid, liquid, or gas? I filtered it in lab, didn't I? It was a solid, yes. Solid formed. Who remembers the fancy word for that? Starts with a P. I gotta give it to you, run out of time. Precipitate. If you see a solid form or precipitate form, that means chemical change. Last thing, gas produced. I know I went quick at the end. Get them all down. Your homework is practicing picking out physical chemical changes. I'll review it again tomorrow. And that's it. So I will go through that again. I just wanted to make sure I get it all down. So this worksheet, front and back, due tomorrow.